Hello everyone, welcome to the lecture of BiCMOS Inverter. In the last lecture we have seen CMOS Inverter and remarks. Now we will see BiCMOS Inverter and its operation and advantages and limitations of this BiCMOS Inverter. You will be able to understand the BiCMOS Inverter operation and its characteristics. The contents of this lecture are starting with simple BiCMOS inverter and then improved versions of the simple BiCMOS inverter we are going to see, and for all these operation and remarks of each and every BiCMOS inverter we are going to see. BiCMOS logic. First, before going to see the BiCMOS inverter, let us see what is BiCMOS logic. BiCMOS logic is nothing but it is the combination of CMOS plus BJT, combination of both, and CMOS is nothing but NMOS and PMOS combination. So NMOS plus PMOS plus BJT is the BiCMOS logic, and in the BJT NPN transistor is used. So combination of NMOS transistor plus PMOS transistor plus NPN transistor will give the BiCMOS logic circuit. In this, the functionality is going to be implemented. That means logic function is going to be implemented with MOS transistors, and output loads are designed with the bipolar transistors of NPN type. So NPN transistors are used to drive the output loads, and NMOS and PMOS transistors are used to derive the logic functionality of that particular logic. Advantages of BiCMOS over other logics are, it is having improved speed over MOS technology and low power dissipation or low power consumption than bipolar technology. And it is having of high input impedance because at the input side MOS switches are used, and it is having low output impedance because at the output side bipolar transistors are used, and it is having of high gain. These are the advantages of BiCMOS logic. Let us see the inverters. There are 4 inverter circuits we are going to see in this lecture. First one is simple BiCMOS inverter, and second one is an alternative BiCMOS inverter with no static current flow, and the next one is an improved BiCMOS inverter with better output logic levels, and the fourth one is an improved BiCMOS inverter using MOS transistors for base current discharge. So from these circuits we can understand that simple BiCMOS inverter is having some problem. So to avoid that problem, alternative BiCMOS inverter is used, and still to improve this alternative BiCMOS inverter, third version is used. Still to improve this, fourth version is used. So starting with the basic circuit and seeing its improvements means each and every circuit is having some problem. To avoid that problem, what mechanism is used in that is nothing but given as an improved versions. Let us see simple BiCMOS inverter and its improved versions. First one, simple BiCMOS inverter. It is the circuit diagram of simple BiCMOS inverter. This figure is showing circuit diagram for the simple BiCMOS inverter. Here simply NMOS transistor and PMOS transistor, combination of these two transistors is the CMOS. Then in the output load NPN BJT and NPN BJT is used. So to drive from T3 and T4, that is NMOS and PMOS transistors, NPN transistors are used. These two are given as the names of T1 and T2. In the output, one load capacitance is showing here. So let us observe the operation of this by applying different values at the Vin value. First, let us take Vin is equal to logic 0. Vin is equal to logic 0. Now what will happen? When Vin is applied as logic 0, PMOS transistor T4 is on and NMOS transistor T3 is off. That is, T4 transistor is on and T3 transistor is off. So, due to the T4 transistor is on, it is acting as a short circuit, and T3 off means it is acting as open circuit. Now, since short circuit is existing, VDD is connected through this T4 to the base of the T2. Therefore, T2 transistor is on, and since it is open, no current is passing to the base of the T1. Therefore, T1 transistor is off. So, since T4 is on, T2 transistor is on and T3 is off. Therefore, T1 is also off condition. Since T1 is off, it is acting as open circuit, and NPN T2 is on, therefore it is acting as a short circuit. So, Vout, this capacitor is having a path to charge to VDD through the transistor of T2. So, therefore, Vout is equal to logic high. Logic high means it is equal to VDD. It is equal to VDD. Actually, its value is Vout is equal to VDD minus VBE, because minimum VBE voltage, that is 0.7 volts, is required to make switch on of this T2. Therefore, VDD minus 0.7 is the output value. So, VDD or VDD minus VBE, these two are representing the logic high. Logic high, that is logic 1. So, for the input of logic 0, output is producing as logic 1. Therefore, this circuit is acting as inverter for the input of 0 volts. Input of 0 volts. Now, let's understand the same circuit by changing the input of 0 to VDD. Apply Vin is equal to VDD. Now, input is equal to VDD. What will happen to the transistors? That is, Vin is equal to VDD. That means that is represented as logic high. When Vin is equal to VDD, PMOS transistor T4 is off, NMOS transistor T3 is on. So, T4 PMOS transistor is off and T3 NMOS transistor is on. Since T4 is off, it is acting as an open circuit, and since open circuit is there, there is no path to send the current to the base of the T2. Therefore, T2 is off. Since T4 is on, T2 is also off. And then, since T3 is on, it is acting as a short. So, this short connection passes the current to base of the T1 transistor. So, T1 transistor is on. So, T1 transistor is on. Since T3 is on, T1 transistor is on. Now, what will happen? Since T2 is off, it is an open circuit. T1 is on, it is a short circuit. Therefore, capacitor is having a path to discharge. So, output, whatever the output is there, previously VDD minus VBE, that is going to be grounded. So, output is equal to, Vout is equal to 0. Or, it is exactly equal to VC sat value, and it is very small value. So, therefore, it can be treated as 0. So, this is equal to logic 0 value. For the input of logic 1, this circuit is producing Vout as logic 0. It means it is acting as inverter for the input of VDD also. So, the circuit is acting as inverter. With input of logic 0, it is producing output of VDD, and with input of VDD, it is producing as output of logic 0. And what about the remarks of the circuit? Here, for the functionality realization, PMOS and NMOS switches are used. For driving of outputs, T1 and T2 are used. That is for the functionality For the functionality, T4 and T3 MOS switches are used, MOS transistors are used, and for output driving, T2 and T1 NPN transistors are used. And then for logic high, it is producing of VDD minus VBE, and for logic 0, it is producing of VCE SAT. So output VDD minus VBE and VCE SAT. Okay. Then circuit is simple. It is having of 2 MOS transistors and 2 NPN. Circuit is simple. Circuit is simple. So it is a simple circuit. That's why its name is given as simple BiCMOS inverter. And next important one is, when Vin is equal to logic high, there is a path from this VDD node through T3, T1, and it is connecting to the ground. So it is nothing but short path between VDD and ground when Vin is equal to 1. So direct path is existing between 2 power supplies. Therefore, static power dissipation is more. Static power dissipation is more. Static power dissipation is more. So next one is, here T2 is off when Vin is equal to high, T1 is off when Vin is equal to low. For these cases, to make discharge of these 2 base currents, there is no path. That is, no base discharge paths. No base discharge paths for the NPN transistors to make the discharge while these 2 are going into the off condition. These are some of the remarks for this simple BiCMOS inverter. Let's see once again these BiCMOS inverter remarks. Important remarks. The inverter has high input impedance because at the input side MOS switches are used. Because of MOS, input impedance is high. Then this inverter has low output impedance since NPN is used at the output side, therefore output impedance is low. And this inverter has high drive current capability but occupies relatively small area. This is the advantage. Then the inverter has high noise margin because having the high input impedance and low output impedance, it will give the high noise margin, and it is having of static path between 2 power rails when Vin is equal to VDD. This is the problem. Then one more is, there is no base discharge path for the 2 NPN transistors while they want to go into the off condition. So these 2 are the problems which need to be addressed for the improvement of this BiCMOS inverter. First one, no static path is existing, so no static path is required, and base discharge path is required as it is missing in this simple BiCMOS inverter. Let's see that. The circuit with improved version, that is an alternative BiCMOS inverter with no static current flow. That means the problem with the previous is, one is static power dissipation is high and second one is discharge path is not existing. To address those 2 issues, first issue, that is static path. To avoid the static path or to don't have any static current in that circuit, an alternative or improved version is represented like this. The difference between that simple BiCMOS circuit to this inverter circuit is simple one, that is T3 transistor drain. In the simple inverter, it is connected to the VDD. Now instead of a VDD, if it is connected to the Vout, then when Vin is equal to logic high, then this T3 is on, therefore T1 is on. So it is having a connection of like this. V out is again having a connection to discharge and this node is disconnected from the power supply. So therefore the change is just remove the drain connection of T3 transistor from VDD and it is connected to the V out terminal. That is the circuit diagram construction change. Now because of this, whether it is working as inverter or not, we will check it. So let's check the operation by taking Vin is equal to logic 0 first. So apply Vin is equal to logic 0. Now what will happen? T4 is on, therefore T2 is on and since it is 0, T3 is off, T1 is off. So CL is not having any path to discharge, it is having a path to charge that is equal to through T2 transistor. Since Vn is equal to 0, T4 transistor is on and T2 transistor is on, V out is equal to VDD. V out is equal to VDD and when Vin is equal to logic high, that is equal to VDD. Here input is applying as VDD. Now what will happen? This T4 transistor is off, therefore T2 transistor is off and T3 transistor is on and T1 transistor is also on. Now output is having a path to discharge through the T1 transistor since these two transistors are on. So that is equal to T3 transistor on and T1 transistor is on. Therefore V out is discharged, that is equal to 0 value. Now what will happen in this case, the earlier problem that is which is existing between these two ground, the static path that is removed. So when Vin is equal to VDD, V out is producing as 0 and Vin is equal to 0, V out is producing as VDD. Therefore these two are complement voltages. So this circuit is acting as inverter even though the drain connection is disconnected from the VDD and it is connected to the V out. Because this path is used always to discharge. Therefore whatever may be the V out value is connected here, it is not a matter because it is disconnected always. Therefore it is disconnected from the VDD and it is connected to the V out value. Therefore the problem which is a static path between the two power rails is eliminated here. Is eliminated. Which is existing at Vn is equal to VDD, the static path, that is short connection between two power rails is eliminated. This is the advantage of this circuit. And what is the next problem we have seen in that? Simple inverter circuit, that is no base discharge path. No base discharge path. Still this no base discharge path is a problem existing in this also because there is no path for this bases of T2 and T1 to discharge while these two are going into the off condition. It is still existing. So what are the remarks for this inverter? The remarks for this inverter are it is acting as an inverter and here when Vin is equal to 0, V out is equal to VDD minus VBE and when Vin is equal to VDD, V out is equal to also VBE. This is the first remark. And second remark is no static path. No static path. Because of that, static power dissipation is reduced. Static power dissipation is reduced. Dissipation is reduced. And next is, since one problem is existing, that is no base discharge path. No base discharge path. It is still continuing. It is still continuing. This is the problem of this circuit. Now, we are going to see the improved version to have base discharge path also along with this static power or no static path. No static path and base discharge path has to be used. So, the improved version when compared to this, we are going to see as the third circuit. The remarks of the second circuit are DC path is eliminated with the help of the changing the connection of drain of T3 transistor to the output connection. Then the output voltage swing is now reduced, which we have seen, that is output for the logic high is VDD minus VBE and for the logic 0 is VBE. So since output swing is reduced, the output because of this VBE 0.7, earlier it is VC sat and now it is 0.7. Since the swing is reduced, speed is increased here. Speed is increased. Means the switching action of the circuit is increased here. The problem with the second circuit is there is no base discharge path. To avoid that problem, to have a base discharge paths, another solution is proposed, that is called as an improved BiCMOS inverter with better output logic levels. Now, the change of this circuit with respect to the previous circuit is just insertion of two resistors at bases of the T1 and at the base of T2 transistor. So, insertion of two resistors is extra to have the base discharge paths. This is only the change of this circuit when compared to its previous circuit. Now, let us check its operation. Same, when Vn is equal to 0, what will happen? T4 transistor is on and T2 transistor is on, T3 transistor is off and T1 transistor is also off. So, because T2 transistor is on, therefore output is equal to V out is equal to VDD minus VBE. And when Vn is equal to logic high, that is Vn is equal to VDD. Now what will happen when Vn is equal to VDD? T3 transistor is on and T4 transistor is off. Now what it has to do? Since T4 transistor is off, actually open circuit, so base of the T2 is not having a discharge path in the previous circuit, but here when this T4 is off, T2 has to be off. Now this base is having a discharge path through the R1 transistor to the ground, and since T3 is also on, it is having a discharge path to the through T3 and R2 to the ground. So, the base of the T2 is having a path of R1 to reach to the ground along with T3 and R2. Therefore, T2 is switching to off fastly because base is having the discharge path. So, it is having the more speed when compared to the second circuit. So, this is off and this is off. T3 is on. Therefore, T1 is also on. Since T1 is on, the CL is having the discharge. So, V out is equal to VBE only, and the switching is faster because of having the base discharge paths. This is the case with when Vn is equal to VDD base discharge path for the T2 transistor. Now, suppose still if input is again 0, when input is equal to 0, what will happen? When input is equal to 0, again T4 transistor is on and T2 transistor is off. So, since T3 transistor is off, T1 has to be off. For this T1 has to be off, this base has to be discharge path. So, this base is having a discharge path of R2 to the ground. So, when T1 wants to be discharged or off, its base is having a discharge path, and T2 wants to be off, then its base is having a discharge path of this. Therefore, basis is having the discharge path. So, system is or the circuit is faster when compared to the earlier circuits. And output swings are VDD minus VB and VB only, and there is no static path connection between the two power rails when Vin is equal to VDD. No static path. That means when Vin is equal to VDD, what will happen? T3 is on, T1 is on, where this is connected to Vout, not to the VDD. So, no static path. Advantages of this are no static path and there is a discharge path. So, base discharge path. Base discharge path exists. But only the problem here is, because of having the resistances, these suitable resistances values getting on the IC is difficult and it occupies more area. It occupies more area. And getting suitable value is difficult over the integrated circuit. That's why again the circuit is modified. So, we are having of improved version as the fourth circuit. Let us see that. What are the remarks? No static path and base discharge paths are available, and because of using the resistances, it takes the more area. Let's see its remarks once again. In the circuit, resistors provide the improved swing of the output voltage when each bipolar transistor is off, because its bases are discharging. Therefore, no VBE also, that VBE is reduced. So, output swings is increased. Then, it also provides discharge paths for base current during the turn off. And the provision of on-chip resistors of suitable value is not always convenient and may be space consuming. That means it may take more area. Therefore, having on-chip resistors is not a suitable solution. Therefore, to have this, to eliminate that problem, those resistors are replaced with MOS transistors. That is nothing but the fourth circuit. See, this is the circuit of improved version over the third circuit. Here, static path exists, base discharge exists. Only the change is the resistors are replaced with MOS transistors. Here, resistors are replaced with NMOS transistors. This is R2 resistor and it is R1 resistor. R1 in the previous circuit is replaced with T5 and R2 in the previous circuit is replaced with T6 transistors. So, resistors are replaced. Resistors are replaced with MOS transistors. Replaced with NMOS transistors. That is, in the place of R1, transistor T5 is used. In the place of R2, transistor T6 is used. Means T6 is on when T1 wants to off. T6 is going to be on when T1 turns off. And T5 transistor is on when T2 transistor turns off. Means T2 want to turn off means T5 is going to be on, and T1 wants to turn off means T6 is going to be on. And only the T1 or T2 will be in the on condition at a time. Therefore, the base of T1 and this T2 are connected as the control signals of the MOS transistors of T5 and T6. So, T2 is switched off means Vin is going to be high. For that Vin, this T5 is on. Therefore, directly that Vin is connected as the T5 gate. And when T1 is going to be turned off means T2 is going to be on. Therefore, then higher voltage will come at this node. Therefore, that is connected as the gate potential for the T6 6 transistor. So this off means, this on means higher potential, it goes to the T6, it's off. Then when this transistor wants to off means input is equal to logic high, therefore same logic high is connected to the T5. Therefore this is off, this is on, therefore base is discharged. What is happening here? T2 is off means, see here, T2 is off means, T2 is off for Vn is equal to logic high since T4 is off. So at that time it is open, nothing is connected, VDD is not connected here, whatever the previous base is there, then this R1, this T5 has to be switched on, so it will goes to the ground connection. That means when Vn is equal to logic high, T5 is on, T2 is off, then whatever the base charge is there, that will be grounded. That is the first one. Then similarly, T1 is off means T1 is off means T2 is in the on condition. Then T2 is in on condition means this is the on means here VDD is connected. So the same potential VDD is connected here to make the T6 into on condition. So once T6 is on condition, then base of the T1 is connected to the ground. So T2 on, then T6 will be on. Similarly, T1 on, then T5 is going to be on. So to have the base discharge paths, these two transistors are used when T2 and T1 are going into the off conditions. So the advantage is there is a base discharge paths provision. Base discharge paths provided. This is the advantage of this circuit. And the two base discharge paths are provided with the MOS transistors. Therefore, they occupy less area when compared to the resistors. And there is no static path also, because the drain of the T3 transistor is disconnected from the VDD and is connected at the Vout. So no static path also existing here. No static path. Therefore, power dissipation is also less in the circuit. So the circuit is advantageous when compared to all the previous three circuits. It is having all the advantages. Let's verify the operation of this circuit by applying input voltage as first logic 0. That means Vin is applied as logic 0. Then what will happen? T4 transistor is on, T5 transistor is off, and T3 transistor is off. T4 on, T5 off, T3 off. Since T4 is on, it is a short. So T2 is on. And since T5 is off, its base is not connected to the ground, it is disconnected. And T3 is off, therefore T1 is also off. At this time what will happen? So because of this short, VDD appears here. That VDD is connected to the T6 transistor base gate. Therefore T6 transistor is on. So when Vn is equal to 0, the transistors of T4 on and T2 transistor is on and T6 transistor is on. This T4 and T2 transistors are on to make the Vout is equal to VDD, and T6 transistor is on to make the base discharge of T1 transistor. So base discharge of T1 transistor there, and because of T4 and T2 on, output is having the charge path, so output is equal to logic high. So output is of having the full swing. Then when Vin is equal to VDD, what will happen? Which transistor is on? So when Vin is equal to VDD, T4 transistor is off, T5 transistor is on, and T3 transistor is also on. T4 off, T5 on, and T3 on. So now what will happen? Since T5 is on, whatever the base is there, that is connected to the ground now. Therefore, since T5 is on, T2 is off and completely its base is discharged. Since T3 is on, what will happen? Previous Vout is connected like this. Therefore, T1 is on condition. Now, what will happen to the T6 here when T1 is in the on condition? This has to be actually off. How it is switching off? Because of connecting the gate to the base of the T2 transistor, it is now open and its base is discharged. So, it is changed from VDD to 0 so that this transistor is off and the 0 is connected to the gate of the T6 transistor. So, now 0 is connected. So, because of this 0, what will happen means T6 transistor is off. T6 transistor is off. So, T6 is off. Therefore, now T1 is in the on condition. So, T1, once T1 is in the on condition, output is discharging. So, output is equal to 0. Now, what is the base discharge path? T5 transistor is providing the base discharge path. So, this T5 transistor is providing base discharge path. Like this circuit will give base discharge path and it produces when Vin is equal to 0, Vout is equal to logic high. Here Vout is equal to logic high through the transistor of T2 transistor, and when Vin is equal to VDD, output is equal to 0 through the transistor of T1. So, this circuit is acting as inverter with no static path, with having of base discharge path, and all the transistors are with of NMOS and PMOS and NP and BJT transistors. So, it takes less area and it is having of IC advantage. See its remarks. In a circuit, the transistors T5 and T6 arranged to turn on when T2 and T1 respectively are being turned off, and it offers high current sinking and sourcing in this circuit. So, till now we have seen BiCMOS inverter with starting with the simple BiCMOS inverter, then 3 improved versions of the circuit. Now, let's check this quiz to have clarity on the understanding of our BiCMOS inverter circuit. First question, in BiCMOS, bipolar transistors are used too. So, in the construction wise we have seen already bipolar transistors are used for the driving of the output. So, that is to drive the output loads, this bipolar transistors are used. Second one, in BiCMOS, MOS switches are used too. Where the MOS switches are used? In the functionality wise. So, for getting the functionality, that is to drive the inputs to perform the logic functions. To perform the logic functions, this is used. The next question, the NMOS and PMOS transistors are used in BiCMOS is of what type? The type is always enhancement mode only. So, enhancement mode transistors. For improved base current discharge, dash enhancement type of NMOS devices have to be used. Means a dash number. In the fourth circuit, how many number of transistors are used to have the base discharge? 2 transistors are used. So, 2 transistors of NMOS enhancement type are used to have the base current discharge. Take these questions as assignment, that is explain BiCMOS inverter operation and transfer characteristics of BiCMOS inverter, derive it and compare CMOS inverter with BiCMOS inverter. Follow this textbook for this topic, that is Pucknell Essentials of VLSI Circuits and Systems. Summary of this lecture is, we have seen 4 BiCMOS inverters, starting from the simple BiCMOS inverter to an improved with no static path and base discharge path also. Till now we have seen BiCMOS inverter circuit with its improved versions. I hope you understood this BiCMOS inverter circuit. Just read it, and if you have any doubts, ask me. Thank you.